Good afternoon. Let me open the afternoon session of the second day of Neutrino Telescopes workshop. This session is dedicated to three commemoration talks of three people that in the early days of the conference gave a great contribute to the conference itself. It's also a way to honor their memory, but also a way to recall the atmosphere, the enthusiasm of these days and the history of neutrino discoveries. So the first speaker is Professor Atsuto SUZUKI, remembering Professor Koshiba. Professor SUZUKI sent us a recorded version of his talk, so we are going to send this video to the workshop.
First of all, I'd like to thank the organizer for the opportunity to show the retrospective on Dr. Masatoshi Koshiba. He passed away in November 2020 at the age of 94. The outline of my presentation is in the following. I will start with brief history up to 1962, exploration of international electron-positron collider experiments, birth of Kamiyakande, Kamiyakande launch, Supernova 1987A, solar neutrinos, original idea of Super Kamiyakande, one more dream, next generation electron-positron linear collider ILC in Japan, and closing remarks. Please allow me to omit honorific titles throughout my presentation. I will start with the brief research history up to 1962. Koshiba graduated from Physics Department of the University of Tokyo in 1951. He demonstrated his own unique character and existence. In this picture of his high school days, he is the only one wearing Japanese kimono. His unique character brought the high school principal to introduce Koshiba to the principal's friend Shinichiro Tomonaga, Nobel laureate of 1965. Koshiba said, "I was a sake drink partner of Tomonaga. Tomonaga was so famous for heavy drinkers." Since then, Tomonaga fully supported Koshiba. In 1953, Koshiba moved to the graduate school of Rochester University. Tomonaga wrote the recommendation letter of Koshiba. In January 1954, Koshiba held a sukiyaki party in his room. This is a very interesting picture of sukiyaki party. Here you can see Richard Feynman and Yoichiro Nambu. Both are Nobel laureates later. On top of that, Feynman and Tomonaga were awarded the Nobel Prize together. It seems to me that Koshiba set up the Nobel Prize of 1965. In June 1955, Koshiba achieved his PhD by phenomena of ultra-high energy cosmic rays and got the research associate position of the University of Chicago. In 1958, he turned back to Japan as associate professor of the University of Tokyo. In 1959, he married with Tomonaga's matchmaker. Friendly relation between Koshiba and Tomonaga continued for a long time. In November 1959, Koshiba was back to US for joining the International Cosmic Ray Collaboration led by Marcel Schein, the University of Chicago. In 1960, he was recommended as a spokesperson of this project because of the Schein's sudden death. In 1962, he returned again to the University of Tokyo after finishing the project successfully. Koshiba's next stage was the exploration of international electron-positron collider experiments. In 1968, the director of BINB, Budgar Institute of Nuclear Physics, proposed the collaboration of the world's first electron-positron collider project, and the collaboration started. Unfortunately, the collaboration was terminated in 1972 due to the Budgar's sudden death. After that, Koshiba moved to DAISY to join the DASP collaboration using the electron-positron collider DORIS in 1973, and then JADE collaboration, Japan, Deutschland, England collaboration at Petra in 1977. Yoji Totsuka, the first Super Kamiyakande spokesperson, joined Doris and Jade as one of Koshiba's group. These activities were taken over by Opal at REP and Atlas at LHC. Koshiba developed a long-term base for successful international collaboration in Europe. Let me move to the birth of Kamiyakande. Koshiba made a big turn in 1979. He proposed the initial concept of Kamiyakande at the workshop on the unified theory and the baryon number in the universe at KK. The proposed detector consists of a cubic shape 2000 ton of imaging water Cherenkov and 7500 5-inch PMTs. However, due to a budget constraint, the total number of PMTs should be squeezed into 1000. This budget was partially funded by the government. After this, the news of IMB project came from US. The IMB detector size is 8,000 ton, and a total of 2,000 5-inch PMTs are installed. Here, Koshiba reached to a tremendous idea of developing the world's largest size 20-inch PMT, collaborating with Hamamatsu TV at the time, now Hamamatsu Photonics. The R&D started in 1979, and in 1981, 20-inch PMT became a reality. At that time, I was in KK and joined this 20-inch PMT R&D as my part-time job. I had another several jobs in KK. In 1981, Koshiba asked me to move to work together in the University of Tokyo. 1 year later, I decided to move from KK to the University of Tokyo. The final design of Kamiyakande, Kamioka nucleon decay experiment consists of 16-meter diameter times 16-meter height cylindrical shaped water tank and 1,000 20-inch PMTs. This is an imaging water Cherenkov detector like this for proton decay and neutrino interaction like this. This detector was constructed inside the Kamioka mine with 1,000 rock overburden. The underground excavation and detector construction started in January 1982 and completed in July 1983. We strongly hoped for such a proton decay signals. When several months had passed after starting the data taking, Koshiba checked this energy spectrum of mu2e decaying electrons. He pointed out, why not lower energy threshold down to 10 MeV? At the time, we used 15 MeV threshold energy in order to detect boron-rayed solar neutrinos. His proposal came from not improvisation, but deep consideration. He had mentioned below, even before the start of the experiment, I had been thinking that the Kamiyakande should produce significant scientific results even if proton decays were not observed. You can see this comment in the paper of the European Physical Journal. This proposal invited the Kamiyakande to solar neutrino detections. However, we had to tackle reducing this huge background mountain. There are three major attempts for upgrading the detector: constructing hermetic live anti-counter, this blue area, upgrading water purification system, and installing the new mud heat time and charge measurement electronics. The detector upgrading started in September 1984. Here shows the trigger rate history as a function of dates of events with energy above 8.5 MeV. Kamiyakande 2 solar neutrino data taking launched in January 1987. In less than 2 months after starting the data taking, a bunch of billions of extragalactic messengers swept through the Earth. On the 23rd of February 1987, Supernova 1987A appeared in the Large Magellanic Cloud. This supernova was the brightest visible one after the Kepler's supernova, which had occurred 383 years ago. Kamiyakande 2 was ready to detect lower energy neutrinos with their energy above 7.5 MeV. From among a bunch of billions upon billions of messengers, Kamiyakande detected 11 neutrino events during 13 seconds at 736 35 of February 23rd Universal Time. This was the first experimental verification of star evolution theory and opened the new research field of neutrino astronomy. Since 1987, Kamiyakande 2 had been accumulating lower energy bands. In 1989, the result of observation of boron-rich solar neutrinos was published. You can see a clear event excess, this red area, around cosine theta sun equal 1. The angle of theta sun is defined like this. The observation was about 1/2 of the standard solar model predictions. Kamiyakande 2 confirmed the solar neutrino deficit, which was originally observed in the homestake experiment led by Ray Davis. The homestake showed about 30% of the expectation. In 2002, Koshiba and Davis were awarded the Nobel Prize in Physics for pioneering contribution to astrophysics, particularly for detection of cosmic rays. We enjoyed a sake party at Kamioka. More neutrinos and more chances to detect proton decays require more light. More light gave a strong motivation to construct the Super Kamiyakande 50,000-ton water Cherenkov detector. In April 1996, Super Kamiyakande data taking started after 5 years for construction. As you know, the 2015 Nobel Prize was awarded to Super Kamiyakande and Snow for the discovery of neutrino oscillations, which showed that neutrinos have mass. The original idea of Super Kamiyakande was given in 1983 by Koshiba. This paper, European Physical Journal, says, as a future major experiment at Kamioka, a large water Cherenkov detector with a sensitive mass of 32,000 tons was proposed in 1983 and presented for the first time at the workshop on Grand Unified Theories and Cosmology, which was held in KK. The name of the experiment was initially called JAC, Japan-America Collaboration at Kamioka. In the autumn of 1983, when the boron-rich solar neutrino studies with Kamiyakande was proposed, Koshiba thought that the event rate was too low for Kamiyakande to carry out detailed studies of solar neutrinos as an observatory. Therefore, in order to really open a new field of neutrino astrophysics, the detector with much higher event rate and therefore a much larger detector than Kamiyakande was required. This was the motivation for Koshiba to propose this detector. This is the title of Koshiba's JAC proposal in KK. The name of Super Kamiyakande was given in the following year in 1984. Highlights show Koshiba's Hyper Kamiyakande idea in 1990s. Koshiba called it donuts, which overcomes less transparency of water and promotes neutrino telescope. Koshiba's one more dream was the next generation electron-positron collider ILC in Japan. The construction candidate site is in Iwate Prefecture, where I am now living. The international IOC design team is working hard. Koshiba contributed to build the Federation of Diet Members for promotion of the ILC. Also, he was an honorary chairman of the Advanced Accelerator Association promoting science and technology. We called it AAA. This AAA facilitates industry, government, and academia collaboration. We are now trying to establish International Preparatory Research Institute. I would like to close my talk with following remarks. Koshiba always worked on his research with keen intuition, passion, and outstanding planning and leadership. His innovative ideas inspired younger researchers who built on his work to realize his dreams. These are two Koshiba's didactic messages. The first one is, a researcher should always hold 3 or 4 eggs. Egg means research ideas at a time, but should regularly ask whether each egg can still become a bird. If not, then the idea is no longer worth holding. So we have to add new egg. The second one is, experimental equipment should incorporate as many distinctive devices as possible. That way, even if you fail to catch the prey you are aiming for, you will have a chance to catch other prey. We pray that Dr. Koshiba's soul may rest in peace. Thank you for your attention.
Thank you to Atsuto SUZUKI for this really inspiring talk. We go on with Serguey PETCOV presenting a commemoration talk about Samoil Bilenky.
Do you hear me now?
Yes, we can hear you.
Okay. So this talk is tribute to Samoil Mikhailovich Bilenky, who was an eminent Russian theoretical physicist. Now, Bilenky was a teacher of a generation of particle physicists, not only in Russia, but also in the former Eastern countries and later in Western Europe. He also he was one of the founding fathers of modern neutrino physics and played a leading role in its evolution to its present advanced state. Here is Bilenky in 2018 at a seminar in honor of his 19th anniversary. Now, a little bit about the background. He was born in 1928 in Zhmerinka, a town in Ukraine, in a family of engineers. He graduated in 1952 cum laude from the renowned Moscow Engineering and Physics Institute. His master thesis advisor was the famous Russian theoretical physicist Yakov Pomeranchuk. The same year, Bilenky got a permanent position at the Laboratory for Nuclear Problems in Dubna, near Moscow, which became in 1956 the Joint Institute for Nuclear Research, and ever since he was a staff member of the Joint Institute. Now, the Laboratory of Nuclear Problems was created in connection with the building of the first Soviet accelerator center in the small town of Ivankovo, which was later absorbed by the newly built science town Dubna, about 120 kilometers north of Moscow on the banks of River Volga. This was a proton synchrotron with energy of about 460 MeV. The accelerator was built in the record time of 2 years and became operational in 1948. Later, in the 50s, a 10 GeV proton synchrotron was also built, and for some time it was the most powerful proton accelerator in the world. The accelerator complex and the laboratory of nuclear problems were classified until 1954. They were called Hydrotechnical Laboratory. Not far there existed a dam with a hydroelectric power plant and Plashatka, the land plot. At the laboratory, a theoretical physics section was formed under the leadership of Pomeranchuk, Isaac Yakovlevich, who was instrumental for the hiring of Bilenky. In 1956, within the Joint Institute, the Laboratory of Theoretical Physics was created. Bogolyubov was appointed director of this laboratory, and Bilenky became staff member of this new theoretical physics unit, and he remained a staff member of this laboratory ever since. Research. Bilenky is an author, co-author of more than 250 scientific articles and 5 books. Bilenky's scientific style is characterized by striving to use model-independent approach to physical problems. In his works, he built bridges between theory and experiment. He obtained his PhD degree in 1957 at the Laboratory of Theoretical Physics at the Joint Institute for application of dispersion relation theory to weak interaction processes. In a subsequent series of articles, Bilenky discovered a general connection between the polarization effects and internal parities of particles in scattering processes, and proposed a method of determination of parities of strange particles, which was later used in experiments at Berkeley at CERN. These articles also initiated the development of the polarized proton target technique in scattering experiments. Here is Bilenky giving a talk at the Joint Institute in the early 70s. And here he's answering some questions during the same talk. Now, Bilenky's most prominent and well-known contributions today are in the field of neutrino physics. In a fruitful collaboration and co-authorship with Bruno Pontecorvo, which started in the early 70s, they developed the theory of neutrino oscillation in vacuum and laid the foundations of the phenomenological theory of neutrino mixing, on which every theoretical model of neutrino mass generation, including GUTS, is based. Pontecorvo, as is well known, moved to the Soviet Union in 1950. In 1952, he joined the Laboratory for Nuclear Problems in Dubna, the same year in which Bilenky became a staff member of the laboratory. Here is Pontecorvo giving a talk at the Joint Institute. Here is him attending a talk. And here is the Pontecorvo and Bilenky working together on a project, on a problem. Now, Bilenky and Pontecorvo wrote about 28 articles together. These are some of the titles. If you look at the number of pages, I mean, usually these articles are very short. The style of the articles is extremely concise. Now, they were the first, actually, to understand in 1975-76 that the properties of massive neutrinos, Dirac-Majorana, and of the neutrino mixing in gauge theories of particle interactions are determined by the properties of neutrino mass term, and more specifically by the symmetries the neutrino mass term and the Lagrangian of the theory have. Later, this idea found its natural realization in gauge theories of electroweak interactions and in grand unified theories. They were the first to consider, for example, the possibility of neutrinos having the so-called Dirac and Majorana mass term, which is at the basis of the seesaw mechanism of neutrino mass generation. This was done in 1976 on purely phenomenological grounds. Later, it was used and is still being used in GUT unifying theory, in GUT theories, unifying the electroweak and strong interactions, and in other non-gap theories employing the seesaw mechanism. The seesaw mechanism not only provides a natural explanation of the smallness of neutrino masses, but via the leptogenesis theory, relates the generation and smallness of neutrino masses to the generation of the matter-antimatter asymmetry of the universe. This is the first page of the paper where this type of mass term at the bottom, at the basis of the seesaw mechanism, was considered. And let me explain very briefly what it was, the content of this paper. Now, they assumed that in a theory, both left-handed and right-handed singlet neutrino fields are present. And in that case, they realized that the more general neutrino mass term would involve a Dirac mass term which connects left-handed and right-handed fields, and Majorana mass term for the left-handed fields and Majorana mass term for the right-handed fields. So the mass matrix has this general form. Now, one can realize this possibility even in the standard theory, which is augmented by, for example, 3 right-handed neutrino fields. In this case, the Majorana mass term of the left-handed neutrino is absent. We have a 0 on this place of this matrix. And if the Dirac mass term is much smaller than the Majorana mass term for the right-handed neutrinos, I mean, this corresponds to the seesaw mechanism of neutrino mass generation. Another article, a review article with Pontecorvo, lepton mixing and neutrino oscillations, was universally used for a long period as a reference article on the subject of neutrino mixing and neutrino oscillations. This is the first page of this article published in Physics Reports in 1977. Now, Pontecorvo was on friendly terms with the whole Bilenky's family. Misha, Bilenky's son, made humorous sketches on the occasion of Pontecorvo's 75th birthday, which are now kept in Pontecorvo's office at the Laboratory of Nuclear Physics at the Joint Institute. And here are these sketches, they are just above the library. On the right, we see Pontecorvo as a magician who picks up one neutrino, then a second one, then a third one from a magical box. While on the left, one sees Pontecorvo, oops, sorry, there was some. On the left, one sees Pontecorvo with secretary Irina Sergeyevna, who is typing his papers, while on the right here is himself riding a bicycle, which he loved very much to do in Dubna, carrying a tennis racket. I mean, he was an avid tennis player, and underwater, a weapon for underwater fishing, which also he enjoyed doing very much. In bubbles, you see the argon, which is produced by solar neutrinos, which interact with the chlorine, and this is a reference to the the famous chlorine-argon radiochemical method proposed by Pontecorvo for detection of solar neutrinos. And on the right, you see the leaning Pisa Tower, I mean, a reference to the place where Pontecorvo himself was born. Pontecorvo also liked very much practical jokes, and his most famous one was played in 1954 together with Migdal Londa on Landau. In the early spring of 1976, I witnessed another one played this time on Bilenky, and probably this was not the only one. Even during the period of collaboration with Pontecorvo, Bilenky made independent, original, and insightful contributions to the development of neutrino physics, and continued to do so after the passing of Pontecorvo in 1993. He was involved in studies devoted to all aspects of contemporary neutrino physics: phenomenology of neutrino mixing and neutrino oscillations, neutrino as double beta decay, the problem of determination of neutrino mass ordering, CP violation in neutrino oscillation, tests of existence of sterile neutrinos at the EV scale, the problem of determination of the absolute neutrino mass scale, and so on. Bilenky wrote also many review articles and lecture notes. One example of this activity, which didn't involve Pontecorvo, is the realization a very important one, of the existence of new source of CP violation in elementary particle physics, more specifically in the lepton sector, related to the possible Majorana nature of massive neutrinos, the so-called Majorana phases. I mean, this idea arose from the observation that if neutrinos are Majorana particles, they are described by Majorana fields, which satisfy the so-called Majorana condition. And actually, this condition is such that it doesn't allow multiplication of the Majorana fields by a phase. This implies that neutrino Majorana fields cannot absorb phases, and therefore, as a consequence, there are more CP violating phases in this case in the neutrino mixing matrix than in the Dirac case. Excuse me just for a second. Now, if you do the counting, it turns out that if you have n families of leptons, there will be additional n-1 Majorana phases. So in the case of 3 families, there is 1 Dirac and 2 Majorana phases, and you can have CP violation even in the mixing of only 2 Majorana fields. It is well known, in the mixing of 2 Dirac neutrino fields, there is no CP violation. In the same paper, another important result was obtained, namely, it was proven that flavor neutrino oscillations are not sensitive to the Majorana CP violating phases. And this implies that oscillation experiments cannot be used in order to determine the nature of massive neutrinos. Bilenky had collaborators in many countries, mostly, but not only, in Europe. An incomplete list is given here, and you can recognize names of people who made important, significant contributions to the development of neutrino physics. For his devotion to the studies of neutrinos, which he usually called exceptional particle, the most interesting among the elementary particles, and in view of the fact that the neutrino properties suggest the existence of new physics beyond the standard model, he called neutrinos a gift of nature. His long-term friend and renowned particle physicist José Bernabéu proposed once jokingly that Bilenky should be called Mr. Neutrino. Teacher and mentor. Bilenky was an excellent teacher, mentor, and inspiration for many young researchers in the field of elementary particle and neutrino physics. His lectures on different topics of theoretical particle physics at Moscow University, where he taught for 30 years, and on neutrino physics at various international schools were always characterized by remarkable clarity. This made him a sought-after speaker, and he was invited and gave lectures at universities all across Europe and in Israel. Here is Bilenky during a visit to SUZUKI. You can recognize Daniele Amati on the right, Roberto Yango, and there are some SUZUKI students and postdocs. And Bilenky also was, attended several of the neutrino telescope workshops, and this is a photo of one of the cases where he was present at neutrino telescopes in the 90s. Bilenky is the author of 5 monographs in Russian and English, which have undergone several editions and which are appreciated by both theorists and experimenters. These are the titles. These books also helped and continue to help many young scientists enter professionally into the fascinating fields of modern particle and neutrino physics. Here are the covers of his books in Russian and English. He started in 1998 and was a tireless organizer of the well-known Pontecorvo Neutrino Physics School. The school had 8 editions so far. The last was in 2019, and became one of the reference international schools of neutrino physics in Europe. Here is the poster of the 2015 school, with again a drawing by Misha Bilenky. You see here on the left upper corner. And this is the poster of the last school in 2019. And here we see Bilenky lecturing at the school in 2015, which was in Slovakia. Now, for his research and teaching activities, Bilenky received many recognitions: the Russian State Medal for Distinguished Service to the State, the International Bruno Pontecorvo Prize, the Humboldt Prize, the Medal of First Degree of the Faculty of Physics and Mathematics of Charles University in Prague, and other prizes. Here is Bilenky in Dubna receiving the Pontecorvo Prize. He's on the right here, from the former director of the Joint Institute, Professor Kadyszewski. Now, I myself was lucky to be a student of Samoil Mikhailovich at the Joint Institute in Dubna in the 70s. And this collaboration, of course, was very highly fruitful and valuable to me. We have co-authored altogether 22 articles, and our last joint article was published in 2017 and actually updated in June of 2020. Here are some of the titles of our joint papers. In general, Bilenky attracted people with his kind and obliging character and had collaborators, students, and friends in many countries. His human warmth and benevolent personality embodied the best humanistic and cultural traditions of the Russian intelligentsia, to which Samoil Mikhailovich Bilenky belonged. Bilenky loved his job, his research and teaching activities. His great interest in physics, the search for new ideas in science, did not diminish throughout his prolific life. He was constantly thinking and working on problems in neutrino physics and more general in particle physics. Bilenky's words were, for a theoretician, there is no retirement. Of his more than 200 paper articles, about 40 have been published in the recent years. And only 3 weeks before he passed, he published a review on the basics of general theory of relativity for beginners, an area which was completely new to him. Here is the first page of this last article of Samoil Mikhailovich. And I will conclude with this photo, which in many senses somehow manage to catch probably the essence of what Samoil Mikhailovich liked most: thinking and working on problems in neutrino physics. Thank you for your attention.
Hi, Sergey. Thank you very much for this commemoration. And thanks that was shown the picture of Samoil at the Neutrino Telescope conference in the 90s. The painting behind him is an original Tintoretto canvas.
Yes, I knew that.
Again, the third speaker is Alexandre SOUSA, commemorating Jacques Schneps, a dear friend not only of the conference, but also of the Padova Department of Physics.
Are you able to hear me?
Yeah.
Yes, very well.
Very good. Okay. First off, thank you very much for the invitation by the organizers to give you this perspective on the life and work of Jack Schneps, my PhD advisor. And also many thanks to the Schneps family and Tony Mann at Tufts for helping to prepare this talk. Jack was born in August 1929 in Peekskill, a small town about 50 miles north of New York City, to a family who had immigrated from Dębice, a small town in Poland. During this time growing up, during the Great Depression and World War II, Jack was helping out in his parents' bakery, which was called the Top Notch Bakery in Peekskill. And then after completing high school in 1947, he enrolled in New York University, where he was commuting every day by train. Growing up, Jack became a dedicated lifelong fan of the New York Yankees baseball team. It was one of his greatest passions. Even after living in the Boston area for over 60 years, where one of the biggest rivals of the Yankees are located at. And one of Jack's favorite tests for people entering his office was actually a pattern recognition test, where he would ask us if we were able to identify him on his grainy picture of a very famous catch that denies Joe DiMaggio and the Yankees winning the World Series during that game. They won it in the last game, but they didn't win it in that game. And I don't think I know anyone was able to complete this test or pass this test. I definitely didn't, but Jack was always delighted to point out that was him in the corner of that picture. Outside of his physics research work, Jack loved singing, loved writing humorous stories, classical music, and also was a lifelong player of the mandolin. And you can learn more about all of those activities in this wonderful video that Jack's daughter Leila put together. After graduating from New York University in 1951, Jack moved to Wisconsin Madison for his PhD studies. And in 1952, he joined the newly formed group by Jack Fry, which had just started at Wisconsin, and he was Fry's first PhD student. His thesis was titled The Production and Disintegration of Hyperfragments, and discussed the interactions and measurements of properties of nuclei containing a bound lambda star particle, which are these so-called hyperfragments. In collecting data for his thesis, Jack used a microscope to analyze emulsion stacks that contain interactions from hadrons and mesons that were produced at the Bevatron, one of the most powerful accelerators at the time at Berkeley, and also cosmic ray interactions from emulsions that were flown in balloons by the US Air Force at that time. And this is an example of about 100 of these events analyzed in Jack's thesis with the K- that then decays into several particles. During his time with Jack Fry's group, one of the highlights that Jack always liked to point out was an event that he found working late at night one day that he could not explain, and then Jack Fry could not explain when you looked at it in the morning. And many years later, so they published this article in 1955. Many years later, Luis Alvarez did a reanalysis of this event and figure out it was an omega minus event observed 6 years before the omega minus was predicted by Gell-Mann, and 9 years before it's discovered at BNL. You can see this is the track from the omega minus decaying into a K minus, and there's a neutral lambda particle somewhere here. And the mass that was attributed to this by Jack and Fry at the time is in perfect agreement with the PDG values that we have for the omega minus today. Perhaps the most important paper coming out of that period from the Fry group was the first evidence of KK bar mixing, essentially by the observation of what we now call the K-long state, long-lived neutral kaon. And this was published simultaneously with what is considered a discovery of this with Ken Landa and Leon Lederman's group at Columbia and Brookhaven. This is just 3 pages before Jack's paper, so it was essentially a co-discovery of this, and these are the events that show evidence that are explained by this long-lived neutral unstable particle. After receiving his PhD in 1956, Jack was invited to become a professor. He received an offer by the recently inaugurated physics department chair, Julian Knipp, there. When accepting the offer, reportedly Jack says, all I need to get underway is a microscope. So him and NIP started immediately to apply for funding and secured what was one of the first university level grants by the Atomic Energy Commission. This was what appears on now like a small amount, only $22,000 grant, but allow Jack to purchase his telescope, which you can see here. He's probably standing next to his microscope, and also allowed hiring new faculty and growing the group. And this was really the first step in building up the Tufts Physics department to where it is today. And this grant is also remarkable in that it has been renewed continuously all the way from then until now, now under the Department of Energy. Somewhere in the mid-60s, a lot of Robinson Hall, the original location of the Tufts department, was occupied by Jack's microscopes and scanning rooms, which was the so-called Tufts Emulsions group, which Jack was the leader of. However, just 2 years after his starting at Tufts as a professor, he, influenced by Fry's accounts of all these wonderful visits to Italy, and after securing an NSF fellowship to fund his travel, he moved to Padova for 2 years to work with Mila's emulsion group, which is shown here, with several scanners and some other faculty. He was mostly interested during that time in the properties of cascades hyperons, which were produced by high energy K- beams at Berkeley. And the activities of this time and also later on are very nicely described by Mila in this review of those years. It is also during this time that Jack met his wife Lucia, who happened to be the only English-speaking staff on the department at that time, and in 1960 they moved together to Boston with him, Lucia, and Laurie. During the 60s, Jack co-founded the Brandeis, Maryland, Syracuse Tufts collaboration, which made extensive measurements of these doubly strange cascade hyperon states, which he had also made in Padova. And this was using data from bubble chambers at PNL, and this is an example of a paper produced by that collaboration, which Jack was instrumental also in keeping together and helping coordinate. Jack went on to use Fermilab's 15-foot bubble chamber, which was the largest bubble chamber in the world and operated between 1977 and 1988. To perform the first precision studies of neutrino neutron scattering in deuterium, and this was the so-called E545 experiment at Fermilab, and using also the Tevatron high energy neutrino beam. He worked with his PhD student Stefan Bilok on measuring interactions of these very high energy neutrinos on neon nuclei, what was called the E632 collaboration. This experience of Jack with the Tevatron high energy neutrino beam, Tevatron source high energy neutrino beam, and emulsions was a perfect fit for the work by the Donut collaboration, which is the same type of neutrino beam, and also a set of emulsions to look for new tau interactions to do a direct observation of new taus. Jack coordinated the Donut muon catcher design and installation, as well as Tufts analysis contributions of the time. And you can see here the microscope that was analyzing these emulsions. It's actually a robotic emulsion scanning, so it happens automatically, much more advanced than Jack's original microscope in 1956, and also an early version of the scanners that were used for the Opera experiment for scanning the emulsions from Opera. Donut reported direct evidence for the tau neutrino in July 2000. They had observed 4 candidates by then, and by the time they ended data analysis, they had seen a total of 9 of new tau interactions. And this is the first candidate they show and the first direct observation of a new tau interaction. And this is the donut collaboration, or part of the donut collaboration at Fermilab in around 2000 with Jack. Despite his interest in neutrino scattering, in those high energy neutrinos interacting with neon, for instance, Jack became increasingly interested in neutrino oscillations, and he joined the Sudanto collaboration in the early 1990s, which, like many experiments at the time, like Kamiyakande, which we heard in the first talk, was originally intended to search for proton decay, but started carrying out measurement of atmospheric neutrino interactions, which were backgrounds for these searches. Jack and his PhD student, Meili Sanchez, produced one of the first Feldman-Cousins analyses of these atmospheric neutrino data and neutrino data in general, confirming the Super K results with the completely different detector systematics and different detector technology. And this is the Sudanto results, and compared to the Super K result, and they're very consistent. In parallel with this, Jack was convinced that neutrino oscillations should be confirmed in a straightforward manner by using accelerator-based long baseline, accelerator-based neutrino beams in long baseline experiments. And this is something he wrote at the third neutrino telescopes, demonstrating how simple it is, and no dangerous models or scenarios are necessary until we can do a confirmation of neutrino oscillations this way. And I note this is 93, 5 years before neutrino oscillations were discovered by Super K. The Minos experiment was the perfect realization of this simple concept, and Minos started in 94. Jack was there from the beginning and started operations in 2005, ran until 2016. And during that time, at the most precise measurement of the large mass square splitting for neutrinos. And even in 2020, is still a very competitive measurement with the current newer generation experiments in that parameter. Jack was also a contributor to the early design decisions for the next generation following Minos, which was the NOVA experiment. And these discussions were starting in 2002. And even after his retirement in 2011, he was always attending the weekly group meetings we had at Harvard, where I was a NOVA postdoc with Gary Feldman, who was the NOVA spokesperson at the time. And Jack remained a visiting scholar there until 2017, and you can see him here at the NOVA control room sometime in 2017 with Lucia and Melissa. During the 2000s, Jack was very interested also in liquid argon TPC technology, which, as we all know, is now the technology of choice for what was LBNE, and now it's LBNF tune. And this is one of the proposals he signed and worked on, which in this case was an off-axis neutrino, an off-axis beam based on a NUMI beam, but with a liquid argon time projection chamber, essentially, maybe where NOVA would be situated. Just 1 year before his retirement, Jack taught himself Mathematica, and as it should be no surprise to anyone, just all by himself, he sanity checked the Dussel LBNE sensitivity studies, and this is an example on the delta CP sine squared 2 theta 1 3 parameter space for normal hierarchy, where you can see in red the curves from Jack's neutrino sensitivity estimates package, and the dots are from the official Dussel globes analysis. Dussel became LBNE a few years later, and they match quite well. We should backtrack a couple of decades to explain, to highlight the next important contribution of Jack to the field and essential contributions for him, and also to the physics department. Jack's career at Tufts spanned an astonishing 55 years since he started until his retirement. And for 9 years of those in 1980 to 1989, he was chair of the TOPS physics department. And during this time, he really was able to establish a thriving graduate program by ensuring stable funding, and also ensure the continued success of the TOPS Institute of Cosmology, which was directed and has been directed by Alex Bilenky since its inception. He did this by securing a $500,000 endowment from the Gravity Research Foundation, which was particularly interested in research that could lead to anti-gravity devices that could prevent things like plane crashes. And this came with a anti-gravity stone, this endowment, which is now part of the graduation ceremony for new students that from the Institute of Cosmology, in this case, Vitaly Venturin, who is now a professor at the University of Duluth. And Jack was part of the committee, so he was in this picture I captured in 2004. During this time as chair, Jack started realizing his vision that high energy physics is an international, highly collaborative endeavor. And so he co-organized the WIN 83 conference at Talois. This Talois has a Tufts pole in France. And did it so with Herbert Pichman and Violette Poisson. And he also pushed and organized the Neutrino 88 conference, for which he was the chair. And here there's an image of Jack as the chair of the conference. Mila was probably chairing the session, and appropriately, according to the proceedings, Vanucci was presenting the possibility of accelerator-based neutrino beams to measure neutrino oscillations. So this is a good summary picture of Jack's interests at the time. A big highlight of that conference was were the first Kamiyakande results, which again we heard about in the first talk. And Tony Mann has a very nice review of the situation of atmospheric neutrino oscillations and the atmospheric neutrino problem on around 2000, which had just been solved by the SUPERK results, but it gives a good account of where things were. In 1998, Neutrino 88, another big topic was, of course, Supernova 1987A, as we also heard it. The Kamiyakande experiment detected 13 neutrinos from then. And I took this picture in 2014 and I was pleasantly surprised. I had not noticed until I prepared this talk that Jack is actually reflected in the picture. But this shows how important the 1987A was, along with all the other topics. And Jack continued to attend all of these neutrino conferences, and he became part of the International Neutrino Commission after organizing Neutrino 88. And at Neutrino 2002 in Munich, Jack succeeded George Marks as the International Neutrino Commission chair. You can see them here together in Neutrino 88. And he stayed in that position for 12 years until Neutrino 2014 in Boston. And this is his first report in Paris, France, of the International Neutrino Commission as chair. And this is just an image of me and Jack at Delphi during Neutrino 2010 in Greece. After stepping down as International Neutrino Commission chair in 2014, Jack wrote this both very informative and humorous at times account of the history of this conference, and I really urge you to read it. I think you'll enjoy it. Even after stepping down from Neutrino 2014, he attended Neutrino 2016 in London and Neutrino 2018 in Heidelberg, Germany, where he was continued to be very active. Here he was chairing the session where Meili Sanchez presented the Nova results, and he continued having scientific discussions and exchanges with his lifelong friends and colleagues like Peter Height and Thomas Patzak shown here, even though this turned out to be his last neutrino conference. Jack has a great love of the Neutrino Telescopes conference. I'll just summarize it in his own words when he was doing a tribute to Mila during Neutrino Telescopes 2013. For me, the year with Mila's group in Padova was unforgettable. I always called Mila my old boss. And when she started Neutrino Telescopes in 1988 and then Nove, she told me I must come, and I've never missed one yet. And indeed, he never missed one as much as he was able to travel there. And this is a picture of Jack with Jack Fry, his advisor, Mila, and Dita in Venice. And also here with Professor Della Porta, who was Mila's advisor, and again, Jack Fry. In 2011, it was my first time on Neutrino Telescopes. We arrived a few days earlier, so I spent some time with Jack and Lucia, visiting Padova and reliving some of his wonderful times during in the 50s, which was also wonderful for me. This is regarding mentorship of students. This is a clockwise chronological subset of the students Jack had, the ones I could track down. It's not easy to do in years before the internet. Jack was really an extraordinary mentor. He was always forward-thinking and insightful in the projects he assigned us. And he was always very supportive in finding and providing opportunities for his students. And more than a mentor, he was also a great friend who welcomed me, and I can speak for Miley as well, welcomed Miley as part of his family. And his family was equally welcome to us, starting from his wonderful wife, Lucia, and his very talented daughters and grandchildren. There's also a great grandson missing here, but there was no space. I'm sure he'll become very talented too. To summarize, Jack was very, very active even after his retirement in 2011, after his 55 years at Tufts as an active researcher at Tufts. So his sudden departure in July 2019 was a shock to all. We knew him and loved him. For those 55 years, he remained a scientific leader in a field that is as rapidly changing as particle physics, which is remarkable. He had a vision of advancing knowledge through fostering of new collaborations and also fomenting wide-ranging scientific discussions. And this was instrumental into developing the vibrant global neutrino physics community that we now enjoy. I hope these slides convey the unwavering love of life that I think all who know Jack knew he had. And this will hopefully endure in all of us through the great memories and moments he shared with us. And I hope we can very soon gather again in Venice to raise a toast to his wonderful life and career. Thank you very much.
Thank you very much, Alex. You really touched me. And thanks again for this commemoration. This session is now concluded. We will reconvene at 3:25 according to our timetable. Thank you again to all the speakers of this very nice session.
Mauro, do you hear me? No.
Yes, we can hear you.
One question. I'm not sure I have activated the video during my talk. Was it activated, actually?
Yes, it was active.
Okay, thank you.
We could see everything.
Okay, thank you. Sorry.
You're welcome. You're welcome. Hello, welcome back to the session. This session is devoted to challenge plenary talks. And the idea of this session is to introduce ideas and suggestions for the future in astroparticle physics. The first speaker of this session is Joseph Formaggio. So I let him to start his talk.
Hello, and thank you for the invitation. I am hopefully displaying this. Can you see that okay?
Yes, they are okay, full screen. You can start.
Wonderful. So, hello everyone. Good afternoon or good morning, depending on where you are. It's my great pleasure to talk a little bit about this challenge topic, and I'll be talking about both direct neutrino mass measurements and coherent neutrino scattering. And if you're a little bit surprised about the two topics that I have, so was I. I received a very nice invitation from Mauro Mazzetto. He says we would like to give one of these challenge talks on new technologies for measuring neutrino masses with neutrino coherent scattering. And to which I reply, that's great. Just, to be sure, are you asking me to give talk on both of these topics? To which he said yes. And I said, okay. So here we go. Two topics. I'll do my best to cover them with the caveat that I have huge biases. And the one unifying theme are these are things that I am interested in. But hopefully others are as well. So luckily, I am starting from the baseline that there are some similarities already on the onset between these two somewhat separate topics in neutrino physics. For one, these are long-standing challenges in neutrino physics and in particle physics. For neutrino mass, and particularly the, whether the neutrino has a mass, what is the scale of neutrino masses, that has been with us for since the dawn of field theory with Enrico Fermi, sketching out in his famous paper in 1934, which after bouncing around several journals, including Science, finally was published. He sketches out the impact of not only how neutrinos and the weak force behave, but also what effect it would have on the spectrum of beta electrons coming from such a decay. And he sketches out whether the neutrino mass is grande, pico, or zero. And that is really the birth of looking at neutrino mass in the method that I will explain today. Not quite as old, but still quite a bit back. There was also in 1974, Daniel Friedman proposed the idea that if the neutrino underwent a weak force with a neutral particle, that it could interact with the entire nucleus coherently. And that would add to the cross-section of neutrinos in a very enhanced way. And so these two early theorists set down the gauntlets for experimental physics in the following decades. Both of these topics discuss the idea of fundamental principles that tell us either about the weak force or about the nature of neutrinos. Obviously, for beta decay, it tells us the mass scale of neutrinos and essentially confirms that there is an energy momentum dispersion in neutrinos, that they don't behave like massless particles. On the flip side, the coherent scattering is really another and important weak probe into the nature of of the weak force, in that it's a small momentum exchange, similar to what you would do for direct measurements. And you're really interacting coherently across the entire nucleus. So both of these are very fundamental principles, one having to do with the nature of the mass mechanism, particularly in the neutrino sector, and the other with the couplings of neutrinos to other particles. The other thing that these two topics have in common is that if you kind of just listen to a high-level talk, the measurements seem amazingly simple if you kind of sketch it out at first. So if we look at, for example, tritium beta decay or any other beta decay, and you wanted to measure the neutrino mass, well, basically the essential tools are you grab an isotope that undergoes weak decays. A favorite among them is either tritium or as we'll see, holmium. And you measure the outgoing electron that comes from the decay, and you measure the electron's energy near the endpoint. And that's where all the information about the phase space and momentum dispersion of the neutrino is really captured. And by just looking at a spectral distortion near the endpoint, then you can extract the information about the neutrino mass. So as long as you have the isotope and you have a way of measuring electrons, this in principle should be simple. I illustrate the case for beta decay, but you can make the same principle for electron capture. And nowadays, holmium is a favorite to look at, one of the most favorable to observe. And the idea is very similar. Instead of trying to measure the electron's energy, you're looking at the total excitation energy that comes from the decay. Coherent neutrino scattering, likewise, in principle, should be simple. If you have a source of neutrinos, the cross section of those neutrinos interacting with the entire nucleus scales roughly with the number of neutrons, and it squares with them. It scales as the square of the number of neutrons. And if you're able to measure the outgoing nucleus as it comes from this interaction, you would benefit from the enhanced cross-section because you get this huge n-squared boost from your material. And therefore, it should be easier to probe than other incoherent processes. So if you kind of write it down, these two topics seem easy to probe. So why has it taken, in the neutrino case, almost 100 years, and we're still not quite there yet, and for coherent scattering, at least 40 years in order to get a detection? And because part of it is that the devil is in the details. I will also say that there is a lot of commonality in the two topics, in that even though they're measuring specific properties about neutrinos, they connect to other aspects of physics, not necessarily about neutrinos. My favorite connection for direct neutrino measurements is their connection to cosmology, and that's because the universe is filled with neutrinos from the early Big Bang that are still there, and cosmological measurements are starting to get to the point where they're at this level of precision that we would expect from beta measurements. And the nice thing is that if these two knowledge about the neutrino mass can inform cosmology, either by giving credence to extensions of beyond the standard model physics, or new physics, such as neutrino self-interactions or dark matter interactions. So there's a lot of connections in knowing what the neutrino mass scale is that applies outside of neutrinos themselves. Likewise, coherent neutrino scattering isn't just to learn about how neutrinos interact with matter, but more importantly, if there are deviations from what you expect from the standard model. And they're an excellent probe because they're assessing these couplings at small momentum transfers, which are usually very difficult to get at with neutrino probes. In particular, you can connect, for example, with looking with anomalous couplings. And in fact, some of the measurements that are made are already making pretty severe constraints on those couplings. The other connection, again, with a different branch of physics and trying to understand how supernovas work and burn, is another outcome of understanding the details of coherent neutrino scattering. And likewise, there is currently a renewed effort in both of these topics that is worldwide. And I point out on the neutrino mass case, there are a number of experiments that are either taking data or in R&D phases. In particular, I'll talk about Catrine, ECHO, Holmes, and Project 8. And all of these have different techniques at which how they get to assessing, how they get to measure the neutrinos at the neutrino mass scale. They roughly fall in these three categories. You can either have the energy from the decay measured in completeness, so a calorimetric effect. And this is the purview of experiments like ECHO and Holmes, which use cryogenic bolometers in order to measure the beta decay of the electron capture of holmium. You have electromagnetic collimators, the Mackey filter technique that was pioneered over 2 decades ago. That is the technique that's used by the Catrine experiment. And then finally, you have a frequency-based method that measures the cyclotron radiation from electrons. And that is the purview of the Project 8 experiment. So each of these experiments in their own way try to measure that spectrum they originally showed in order to get exquisite precision, but also enough sufficient statistics to access whether the neutrino has a finite mass. And all these experiments are either ongoing now or are in the R&D stages all over the world. And likewise, there is a similar worldwide effort. In fact, I didn't list every single one of them. I just listed a few. Also trying to measure coherent neutrino scattering out there from a variety of sources and a variety of methods. They roughly, the ones that I will talk about, but it's by no means comprehensive, include ionization detectors. These include experiments like KONOS and Texono. And then cryogenic bolometers, which are a little bit more in my wheelhouse, and that includes minor, ricochet, and nucleus. In the former, you have large, massive detectors. So you have a lot of mass that you can use. The energy thresholds are at the keV scale. Another approach with these cryogenic bolometers that go down to millikelvin temperatures is to get very, very small detectors to reach much lower thresholds. And a few of them either have tagging of backgrounds that are coming in externally, or some of them actually do particle identification in situ. Now, why has there been this worldwide effort? In part, it's because there's been some real breakthroughs in both of those fields in the last two decades. For one, we now know that neutrinos have mass, and so that sets a bottom scale for measuring neutrino masses, and that's part of the motivator behind these neutrino mass experiments. And I'm happy to say that just this past year and a half, the Catrine experiment, which was started in mid-2000s, has finally released its first results at the end of 2019. You can see a picture of the Catrine experiment in Germany as it's being unloaded and about to set home, and the picture above. And over after it's been installed over almost 10 years of getting it commissioned and up and running, The Catrine experiment has released its first data. Just a glimpse of what it could do, just a few basically days of data shows excellent agreement with the beta spectrum that you would expect, and has already in that short time period established a neutrino mass limit at the 1 eV scale. Even better news on the coherent side, because the coherent experiment recently has also not just set a limit, but made a discovery. Just about 4 years ago, the coherent experiment at the spallation neutron source observed the reaction for the first time at energies of order 30 MeV of neutrinos coming in. And more recently, they've released not just the cross-section from their first experiment with cesium iodide, but now have done it also with argon. And they're proceeding to add more and more isotopes as we speak. So this is really a great beginning for a measurement of this sort after many decades of trying to get it done. Now, we're not stopping here, of course. Both programs have very ambitious goals, and I'll list a few of them now. For the neutrino mass scale, and over the next few years, I think the Catrine experiment is well poised to make a measurement at the sub-eV scale, basically removing what's known as the degeneracy scale. But its ultimate goal is really to make a positive measurement of the neutrino mass, not to just set limits. And so the next ambitious goal is to push down to the inverted ordering scale, which is of order tens of milli-eV. That's a quite ambitious goal for an experiment, future experiment. On the other side, we want to move to the case where we want to detect lower and lower energy neutrinos from coherent neutrino scattering, almost to the point where we're sensitive at the level of solar neutrinos, which incidentally was one of the original ways of studying solar neutrinos that was proposed back in the 80s. That's a very ambitious goal as well, but certainly one that is motivating a lot of the science and the experiments that I mentioned before. So I will provide a little bit of my own thoughts on the technology that's being used to get there. And basically, both experiments have to overcome three major things, and this is common to all of them. They need sufficient statistics in order to access the region that they aim to probe. Background reduction is a key factor in extracting the signal. And in both cases, you need exquisite energy resolution in order to say something about your signal. So part of the reason is because for beta decay, you really need to look at the endpoint of the spectrum in order to extract information about the neutrino mass. The last fraction of the EV has very little of the spectrum that comes from the decay. So you can have an extremely hot source. That's not terribly hard to find, but you still need sufficient source and at high resolution in order to extract a signal for beta decay. And so you're fighting insufficient space at this level. In the case of coherent scattering, you have the enhancement from the cross-section. However, that said, we're still dealing with neutrinos and their cross-sections are very small. So there are two ways to go about it. One is that you operate at high energies, and this has been a strategy of the coherent collaboration. And in fact, in doing so, they've been able to extract the first positive signal for coherent neutrino scattering. But you can opt to go to lower neutrino energies and where the coherence effect dominates. And at that point, you need much larger fluxes because the cross-section is falling like the energy squared. And nuclear reactors, fortunately, appear to be an excellent source to overcome this. Now, so you need sufficient statistics, and having super hot sources on the beta decay end, or going to large fluxes like reactors is a common strategy for several of these experiments. The other, of course, is also trying to overcome backgrounds. So every time that you propose a new technique and you push it down, you discover new backgrounds. On the left, you can see the Catrine spectrum again, and you note that there is a background there. Most of this is coming from radon, which is a common background for rare decay experiments, but was not entirely predicted for Catrine, since it's not a rare decay experiment. But another background that appeared are these Rydberg atoms, these excited states that come into the spectrometer and decay and release an electron, which looks like our signal. So every time you push the technology to the new order of magnitude, you're optifying new backgrounds. On the right, as we push down lower in energy, we find that there is further and further backgrounds. I show here the plot from actually the CREST experiment, just to show the background wall that many of these types of cryogenic detectors have to face when they push to lower thresholds. And they have different strategies for overcoming this. On the left-hand side, you have direct measurements that use optimized magnetic fields or removing the radon altogether to get around these backgrounds. For an experiment like Project 8, you have magnetic shielding from surfaces. On the SEN side, they use either passive or active shields in order to tag events, or in some cases, actually discriminate between electron and recoil backgrounds, which is a big legs up in trying to extract a signal. All of these are different strategies for removing this notorious background. All of these experiments also benefit from having exquisite energy resolutions. Here I show Catrine, the ECHO experiments, which are these cryogenic bolometers, and Project 8. All of them are reaching at the EV scale energy resolutions now achieved by these efforts. And energy resolution is common also to the coherent scattering measurements. That's because energy resolution translates into lower and lower thresholds. And part of the way this has been done is by going to these very small bolometers where you try to access basically the lowest possible excitation states of your crystal, which allows you to go to these super low thresholds. I'm showing here some of the work from Nucleus, which has really achieved spectacular energy resolution. And a similar results from other collaborators in at Northwestern with extremely low EV scale resolution on these kinds of detectors. And this is just to illustrate where the technology is going. And in many cases, actually, there is actually common technology that's being used for both. And I'll highlight a few of them. For example, for experiments like HOMES and ECHO, which are these cryogenic bolometer experiments where they measured the heat on exuded by the decay of holmium-163. They use either transition edge sensors or magnetic calorimeters in order to measure these small changes in temperature. Well, that technology is exactly the same as is used by experiments like Nucleus and Ricochet, among others, where you're operating at extremely low temperatures and you're trying to measure these changes in energy. So in some cases, the technology is actually shared between the two collaborations to some degree. And as I mentioned, a lot of these experiments, by going to these small cryogenic models, go to very small detectors. So, but you're still dealing with neutrinos where you need high statistics. So that means that instead of one giant detector that you're detecting these events, you now have many, many little detectors that you're reading out. And so the question of how do you deploy and measure a myriad of different detectors in one cryostat becomes quite challenging. And the use of multiplexing, and I have a personal favorite, which is RF multiplexing, but it's not limited to that, are the kinds of techniques that are used both by neutrino mass measurements. Here's a picture of ECHO and their MMC readout, but also in experiments that read out transition edge sensors for large scale bolometers that are used for SENS experiments. And then finally, many of these experiments have to operate at near the quantum limit, and using amplifiers and technology that works at these scales near the quantum limit has become more and more pressing. I illustrate one example. This is the Project 8 experiment, which uses microwaves in order to detect those electrons. And we get much better performance were we able to operate at the quantum limit. And traveling wave parametric amplifiers are one technology that the experiments could use in order to achieve these low noise limits. So you may have noticed that there is kind of a sense that there is shared technology between many of these projects, but not all. A lot of this is actually spurred, luckily, by an effort in a completely different science field, which is in trying to get quantum sensors and for quantum computing at their highest levels. So this includes the ability to produce high levels of Josephson junctions at mass scale, improving superconducting devices and wiring, and basically the infrastructure that one would need in order to operate these experiments either at extremely low cryogenic temperatures or near the quantum limit. And this is very exciting because these are new opportunities for these experiments to probe, allowing them to surpass some of the obstacles that they have. However, they bring their own challenges. And so I want to leave this talk with some questions, perhaps for the audience to ponder. One of the big questions is really, do these technologies scale? Right now, the experiments are sort of at the few tens to maybe a few hundreds. I would say maybe the ECHO and Holmes experiments being the most aggressive, with thousands of channels being planned. And the question is, can the technology scale in a way that makes sense for these experiments to achieve their goals? The second is that all these experiments are operating in somewhat harsh environments. For the case of the SENS experiments, especially the ones at reactors, they're exposed to a lot of unwanted neutron backgrounds, for example, and they often have to operate on surface. So that's quite a challenging place to work if you're looking for rare events. Furthermore, many of these experiments that I showed are cryogenic experiments. That itself is a harsh environment. And it's not an easy place to just switch things out and operate and present unique challenges. And one of those challenges that could come up is, of course, what backgrounds are going to lurk at the next level, at the next scale of these experiments. They're often involving new technologies, new sources of material. We don't know what kind of backgrounds we'll be susceptible to. And so an exploration of those backgrounds in these new environments is going to be key in order to make several of these efforts pay off. So, but I want to leave with the idea that at least why I do these two very different experiments is because they're hard. And sometimes difficult problems are the most fun to tackle, even though they carry the highest risk. And so I quote a president that is not the crazy one that we just had, that sometimes we do things because they're hard and worth doing because they're hard. And with that, I have spoken enough, and I thank you for your attention.
Thank you very much for your talk and also for the question that you left to the audience. I encourage the attendees to put some question in the question and answer panel. Up to now, I see no question. I recall you that you can continue the discussion that was opened by Joe on the Slack channel of the plenary session. I invite you all to put questions also there. Thank you to the speaker again, and we can move to the next one. That is Joachim Kopp.
Okay, you should now be able to hear me and you should be able to see my slides.
Yes, correct. You can start.
Okay, so first of all, let me thank the organizers for inviting me to this very interesting conference and for talking to you about neutrino masses and mixing's theoretical challenges, which is a great topic because I only have to talk about the challenges and not about how to solve them, because for that, of course, we should all go to the parallel sessions where the real experts will be talking about how to solve those challenges. And second, there are, of course, way too many challenges in neutrino masses and mixings to cover them all. So I had to make a choice, and I apologize in advance to all those whose challenge is maybe not addressed in sufficient detail in this talk. So the 4 challenges I'm going to talk about in the next 25 minutes or so is the challenge of understanding neutrino interactions, the challenge presented by oscillation anomalies, the challenge of collective oscillations, and the challenge of new physics in the neutrino sector. So let me start with challenge 1, understanding neutrino interactions. This has become a very pressing issue in the context of current and near future long baseline experiments. Now, I thought it would be bad to start the talk by showing a picture of one of the experiments and not of the others. So I have removed all the labels from this plot and will put generic labels there. And in doing so, I will address one criticism that particle physicists often face, namely that our experiments don't have good acronyms, right? For instance, the cosmologists, they say, look, we have experiments that are called Holy Cow and Polar Bear, whereas some of the most successful experiments in particle physics were called D0 and L3, which certainly didn't do justice to the great physics that came out of those experiments. So in this very generic neutrino oscillation experiment that I'm showing here, we start here on the right-hand side with an accelerator, which I'm going to call Macaroni, which stands for Mega Accelerator for creating abundant radiation of neutrini. So that's the neutrino source. It starts with high energy protons that are dumped onto a target, produce lots of mesons, mesons decay, making neutrinos. Then the next stage is the near detectors. We're going to call them, for the purpose of this generic experiment, we're going to call them entrecôte, which stands for experiments needed for tackling reliably the extreme conundrum originating from theory errors. So basically, these are the detectors that are there to measure the initial unoscillated neutrino flux and constrain neutrino interactions, because these are 2 challenges that we can treat theoretically only with very large errors. Finally, far, far away, where far, far away means at least a few hundred kilometers, we have the far detector, which we are going to call Gelato, which stands for Ginormous Experiment at Long Baseline Aiming to Test Oscillations. That's, of course, the main detector, which then measures the oscillated neutrino flux. Now, in order to extract physics from these experiments, of course, we have to understand how neutrinos interact. To some extent, the near detector suit aids in this, but there's always situations where theory input is needed. And that's the first challenge that I want to address here. The large systematic uncertainties in the composition of the neutrino beam, and in particular in the neutrino interaction cross-sections. So let me explain what the difficulties are here. So these pictures here, which I've taken from Callum Wilkinson, show the different stages of a neutrino interaction. There's, of course, the hard interaction of a neutrino on a nucleon. That in itself is difficult because a nucleon is a composite particle. Even more problematic, we don't even know the initial state of the nucleon, because the nucleon is bound inside the nucleus and we don't know its wave function, at least not exactly. Second, the nucleon is not on its own. Inside nuclei, nucleons tend to pair up. So if there's a neutrino interaction in one of the paired nucleons, one feels the effect of the partner. And finally, even after the primary interaction is over, the interaction products have to get out of the nucleus and experience final state interactions, which are again hard to model. So this initial stage, the interaction on a single nucleon, has traditionally been classified into three different regimes: the quasi-elastic regime, where the neutrino scatters on the nucleon as a whole; the resonance regime, where the neutrino interacts on the nucleon and excites the nucleon into an excited state, which then decays, for instance, by emitting a pion; and the deep inelastic regime, where the nucleus basically gets completely disintegrated in the neutrino interaction. The first and last regimes are somewhat easier to treat theoretically, the quasi-elastic one, because the nucleon can be treated as elementary, and the deep inelastic one, because we have parton distribution functions to describe the nuclear structure. The resonant regime is quite difficult. And even more important, I've mentioned before that these multi-nucleon effects have become important. So over the past decade or so in particular, progress has been made in modeling so-called two-particle, two-hole interactions, which are interactions that involve not one nucleon, but two nucleons. Another way of looking at this is this plot here, which shows schematically the cross-section as a function of the neutrino energy. You see on the right-hand side, the deep inelastic regime, then the resonance production regime. And here in blue, the quasi-elastic regime. If this was really true quasi-elastic scattering, this would just be a single peak. However, there are multi-nucleon effects. There's other effects like the giant resonance, for instance, and therefore there's this broad bump here. And this is what's really difficult to tackle. Now, I already mentioned that one way of mitigating these problems are using near detectors, especially nowadays, near detectors that are placed both on axis and off axis in order to disentangle the uncertainties in the flux and the uncertainties in the cross sections. Of similar importance are hadroproduction experiments, like for instance, Na61 SHINE, which test directly the spectra of all the mesons that come out when protons are dumped onto a specific target material. Now, these experiments help greatly in mitigating the problem, but there's always situations where theory is needed. For instance, the extrapolation from the near detector to the far detector is never trivial. It's one of the most non-trivial challenges in long baseline neutrino oscillations. And so certainly a better modeling of neutrino interaction is like the foremost request from theory that my experimental friends usually name when I ask them, okay, what do theorists need to do next? Second, I think that another way in which theory can help is by developing new strategies for optimally exploiting near detector data. For instance, in a setup like Dune Prism, which takes data at different on and off axis angles, just doing this disentangling of flux and cross-section uncertainties is again a highly non-trivial task. So this brings me to the second challenge that I wanted to talk about, namely oscillation anomalies. We've already heard a little bit about anomalies in previous talks. Let me just mention again, the anomalies I'm talking about mostly here are the LSND and mini-Boon anomalies, both experiments that have observed an anomalous appearance of electron neutrinos in a muon neutrino beam. And there's also the reactor and gallium anomalies, which have seen anomalous electron neutrino disappearance. And now most recently, there's also the neutrino 4 anomaly, on which Carlo Rubbia has talked yesterday, on which there will also be a talk by Anatoly Zerebrov from the collaboration on the 25th. So what's common to all these anomalies is that the distance between the neutrino source and the detector is too short for the anomaly to be explained by standard model oscillations. So very early on, people have started thinking, oh, maybe we are onto something new here. Maybe there's more than 3 neutrino flavors. At the phenomenological level, that's an easy thing to do. One just expands the neutrino mixing matrix from a 3x3 matrix to a 4x4 matrix. And then the oscillation formalism goes through as before. More detailed model building is a different story. Now, what's interesting is that in a certain limit, the oscillation probabilities take a very simple form. For instance, the electron neutrino survival probability in this limit depends on just one parameter, namely the PMNS matrix element UE4, which is the mixing between electron neutrinos and sterile neutrinos. Similarly, the muon neutrino survival probability depends only on U mu4, the mixing between sterile and muon neutrinos. And finally, the mu to nu e conversion probability depends on the product of the two. So even in this highly oversimplified picture, we have 3 observables for only 2 variables, so the system can be overconstrained. This is done in particular in the context of so-called global fits, which are carried out by a number of collaborations worldwide. And here's a result from such a fit. So what's shown in this plot is on the horizontal axis, the mixing between muon neutrinos and sterile neutrinos, and on the vertical axis, the delta m square, the mass squared difference between the active neutrino states and the hypothetical sterile state. Now, if we take the anomalies at face value, then the fits show that the parameter space of the model would need to lie somewhere in these red regions here. On the other hand, if we then look at muon neutrino disappearance, which is the one channel in which no anomalies have been observed, then this channel forces the parameters to be to the left of the solid black line here. So you see that there is severe tension. So clearly this simple picture does not work. One can quantify this and one then ends up with a p-value less than 10 to the minus 4. So clearly just adding a sterile neutrino does not work in explaining all the anomalies. It might still work for explaining a subset of them, but not for all of them. So what can we do? As theorists, phenomenologists, of course, the most exciting possibility may be that there is something even more elaborate than just a single sterile neutrino. And in fact, the archive is abundant with proposals. I'm just highlighting a few of them here, most of them in the context of the mini-Boon anomaly specifically. All of them involve sterile neutrinos at one point, but then also other particles. And typically the sterile neutrinos are then also often heavier than the ones that would participate in oscillations. For instance, sterile neutrinos, so at the MeV scale or so, could be produced in the target, then travel to the detector and decay there radiatively. Since mini-Boon cannot distinguish a photon from an electron, such a single photon would look very similar to a charged current nu E interaction, which is mini-Boon's oscillation signal. Similarly, the sterile neutrino could also be produced directly in the detector, followed by a quasi-instantaneous radiative decay. The sterile neutrino could be produced in the detector and decay via a dark photon. Or the sterile neutrino could be produced in the target and then decay back to an active neutrino in flight, and those active neutrinos could make the signal. All of these scenarios have their virtues and their drawbacks. It just shows that there is a lot of theoretical activity and that we're still searching for an explanation for these anomalies. Now, of course, many of you will ask, well, why is he talking about new physics models? We should first understand the standard model physics, and that's a fair enough comment. So let me talk about standard model physics, in particular in the context of mini-Boon. Here's once again the mini-Boon spectrum showing the clear axis above the backgrounds. And I just want to give you a flavor of what the standard model challenges are that we face in understanding such data. So let's, for illustrative purposes, focus in particular here on this light brown background, which arises mostly from delta resonance production. So neutral current neutrino interaction in which a nucleon is excited to a delta 1232 resonance. The delta resonance mostly decays to a pion, but there's a rare decay mode that produces a photon. Once again, we're in a situation where mini-Boon, not being able to distinguish photons and electrons, would regard this as a potential charged current nu E interaction. Now, of course, mini-Boon are doing whatever they can to extract this background from data. And in fact, the delta production rate can be measured by exploiting the dominant decay mode to a pion. So the control sample is deltas decaying to a pion, where the pion is observed as a pion. Now, this sounds simple, but it's not so simple. The reason is that those pions are still produced inside the nucleus. So as the pion propagates out of the nucleus, it may get absorbed. It may either excite another delta resonance. In this case, that we would now have, rather than one delta resonance, we would have 2 delta resonances. So the likelihood that one of them decays radiatively is enhanced, which leads to an increase in the background prediction. Or the pion may just be absorbed without leaving a trace. In this case, the data sample in the control region would be suppressed. And once again, this would lead to an enhancement of the background prediction. These effects have been recently studied, for instance, by Ionisian, Giunti, and Ranucci. And they have also been investigated by the mini-Boon collaboration themselves. They are being taken into account in the mini-Boon fit, But of course, the problem is that this is now a point where one has to rely on theory. And theory in this business comes with large uncertainties, which are unavoidable and hard to quantify. So these are the kind of challenges that one has to address. And these are the kind of processes that we need to understand better if we want to get to the bottom of some of these anomalies. Okay, so from my point of view, the to-do list for the community, especially for the theory community here, is to further scrutinize the anomalies for unknown systematics. The problem is there are at least 4 different anomalies now, and they're all based on very different experimental technologies. So we would need 4 independent standard model effects. Second, perhaps we should also scrutinize the null results a bit more. We're always ready to believe in a result that is consistent with the standard model, while being extremely skeptical about results that disagree with the standard model. Maybe sometimes the null results deserve the same level of scrutiny. I should, however, say that for none of the null results that I showed, there is any doubt that there might be something wrong with it. And even if there was, removing a single null result from the global fit would not be enough. One would need to remove at least 2 to significantly improve the fit. And finally, as theorists, we're hopefully permitted to also think about extended models and dream a bit. Okay, this brings me to the third challenge I wanted to address here, namely collective neutrino oscillations. This is another point where I can mention one of the advantages that astrophysics has over particle physics, namely astrophysics always has cool pictures and movies to show. So I managed to sneak one of those in here. What I'm showing here is one of the famous supernova simulations from the Munich group. You see here what happens just a few hundred milliseconds after core bounce. You see this highly turbulent dynamics of the material inside the supernova core. So clearly a very, very complicated environment. And in this environment, there are abundant neutrinos. And these neutrinos are going to be one of the main signals that we are hopefully going to detect from the next galactic supernova. So it's extremely important to understand how these neutrinos behave. Now, as you know, neutrinos, when they travel through ordinary matter, they experience matter effects. Here we are in a situation where the neutrinos themselves are so dense that they create a matter effect for the other neutrinos. So it's a highly nonlinear system. That can be seen from this equation here, which is a form of the von Neumann equation, the evolution equation for the density matrix. What we have there on the left-hand side is essentially some kind of Liouville operator. And on the right-hand side, we have the commutator of the Hamiltonian with the neutrino density matrix. So the neutrino density matrix basically describes for a given neutrino momentum mode how the different flavors are occupied and how they are mixed. The Hamiltonian in turn consists of 3 pieces. There's the vacuum oscillation piece, which has the familiar form, m²/2e, sandwiched between the PM and S matrix. There is the standard MSW piece, which is proportional to the net electron number density. And there is the self-interaction piece. First, this piece contains an integral over all the neutrino modes. So we now no longer have just a differential equation, but we have an integral differential equation, which at least scares me when I see it. We see that it's highly nonlinear because the density matrix now appears both in the Hamiltonian and outside the Hamiltonian. So clearly that's going to be a very complicated system. But what one can already see at this level is that in the limit of very, very high neutrino densities, so in the very inner core of the supernova, this last term is going to dominate. And this last term does not depend on the modulus of the momentum p. This means that all neutrino energies are oscillating more or less in unison. This is what's called synchronized oscillations. On the other hand, we see that there is a non-trivial angular dependence, which means that we cannot get away by trying to simulate this in one dimension or so. So this is really a highly non-trivial numerical problem. And it comes with all kinds of instabilities and poses formidable theoretical challenges. On the other hand, it's a pure standard model problem. So we know that this physics exists, so we had better understand it. And solving it will be crucial to optimally exploit the signal from the next galactic supernova. And this is indeed pressing because the neutrinos are already on their way. We know that the next galactic supernova must already have exploded. The neutrinos are on their way to us. And by the time they get here, we should have as good as possible an understanding of how they oscillated on their way out of the supernova. Okay, now finally the fourth and last anomaly, challenge that I would like to address here is new physics in the neutrino sector. We have not conclusively discovered new physics in the neutrino sector yet, but there's a broad research program searching for it. And obviously I cannot cover all of it here, so I'm starting with perhaps the most generic way of describing new physics, namely an effective field theory. Below the electroweak scale, some often discussed effective operators look like this, for instance. So these are effective 4 fermion operators, so dimension 6 operators. They can be either of the neutral current type, which means they couple 2 neutrino fields to 2 other standard model fermion fields, or they can be of the charged current type, where they couple a charged lepton current, or current converting a neutrino to a charged lepton or vice versa, to another charged standard model current. The Wilson coefficients of the operator are typically written in terms of some dimensionless couplings, which tell us how strong the hypothetical new interaction is relative to standard model weak interactions. If we consider neutral current interactions, the main phenomenological effect will be non-standard neutrino matter effects. If we consider charged current interactions, these will modify the way that neutrinos are produced and absorbed. And of course, what I'm doing here can never cover all kinds of new physics. For instance, effective field theory cannot cover the physics of light sterile neutrinos, of neutrino magnetic moments, of so-called secret neutrino interactions, of neutrino dark matter interactions, and of quite a number of other effects. I won't go into detail on those, but we can see on the program that there is an abundance of talks by excellent people that are going to address some of these challenges. Now, what I want to talk about here is a new kid on the block, a new experiment, namely the phasor experiment at the LHC. You can imagine that the LHC is an abundant source of neutrinos because it's an abundant source of mesons, and mesons decay to neutrinos. And now, as soon as the LHC restarts, we will have a detector to observe those neutrinos. That's the phasor nu detector, which is placed a few hundred meters downstream of the Atlas interaction point. And I should say that phasor is one of those cases where even particle physicists came up with a good acronym, in my opinion. So here's an example of what phasor can do. This is a preliminary plot of a sensitivity study that shows constraints on a large number of effective field theory operators. The colored bars here show you what phasor nu can do, and the arrows here show other constraints. And you can see that for some of these operators, phasor nu really is ahead of others. So we will really learn something new, and we will probe new physics scales that go up to tens of TeV or so for some cases. Now, one question that people often ask in the context of non-standard neutrino interactions is, well, it's good to write down these operators, but is it possible to actually write down a UV complete model that would saturate the anticipated constraints? So is there any realistic hope for discovery? I can here just say that the answer is yes, for some cases. And I won't have time to go into detail, but I have a backup slide on that in case people are interested. Now, finally, I would like to mention the physics potential of the near detectors at neutrino facilities. This is the Dune near detector complex. It may also be able to do interesting physics on its own, of course. And finally, there is a movable platform that allows the 2 argon detectors to be moved in and out of the beam axis to take data both on axis and off axis. Once again, this is done in order to disentangle the flux and cross-section uncertainties. Now, once again, slight criticism here. The acronyms ND-LAR and ND-GAR can certainly be improved upon. And here's my proposal. Let's call them Lagoon for liquid argon gadget for on and off axis neutrinos, and Seaside for system of evaporated argon for systematics, interactions, and detailed event topologies. Because that way, with Sand, with Dune, with Seaside, and with Lagoon, we can give talks that evoke nice memories of beach holidays. And it's always good if we get the audience into a nice mood, I think. Okay, now just to show you one example of what can be done with the Dioneer detector, this is a sensitivity study for heavy neutral leptons. In this case, in particular, heavy neutral leptons coupled to tau neutrinos. The colored region here is the region that can be covered by the Dioneer detector after taking data for just 5 years. The gray region up here is what has been constrained already by the CHARM experiment. And the other lines here are the sensitivities of other proposed experiments. I should, however, say that at the present stage, the Dioneer detector, of course, has the advantage that it's actually going to be built in all likelihood, whereas the others are still a bit more virtual, perhaps. So what we can see here is that the Dioneer detector will be able to cover significant new parameter space. And we can also see by comparing the solid and dotted curves here that this technique of taking data both on axis and off axis, this benefits not only the standard model physics program, but it also benefits new physics searches. That's because the signal of a heavy neutral lepton in the MeV scale is typically more spread out in angle than the standard model neutrino background. So the signal to background ratio increases as one goes off axis. Okay, so I think in the context of new physics in the neutrino sector, it's the task of the theory community to fully explore the potential of upcoming experiments for BSM physics. And by doing so, to make the statement that neutrino oscillation experiments are not single purpose detectors anymore, right? We are no longer measuring just a single mixing angle and a single mass squared difference. These are really multi-purpose observatories, not so unlike the LHC, in fact. So this brings me to the end of my talk. For the summary, I leave you once again with the list of the 4 challenges that I mentioned here, and with the pictures of some of the junior people who have contributed to the work that I've shown here. Thanks a lot for your attention. And I'm of course happy to answer questions either here or on Slack.
Thank you very much for the very nice and comprehensive review. There is one question from Marco Laveder. Marco, you are allowed to talk.
Thank you. Hi, Joachim, very nice talk. You didn't mention the 5 MeV bump at the reactor, even if at some level you have a model to explain it, right?
I don't have, no, my student does.
Ah, okay.
Vedran here in the upper left-hand corner. He has like, I think this is the only BSM model that could explain the 5 MeV bump, but I'm not on that paper.
Okay.
But yeah, I didn't comment much on the physics of reactor neutrinos here. But of course, there we are in a similar situation to Mini-Boon. There's on the one hand, formidable standard model challenges that we have to overcome. Well, and on the other hand, the exciting possibility that we may really be onto something new, but well, we first need to understand the standard model physics, of course.
Okay, but perhaps we can wait to Patrick Huber to give the talk about the 5 MeV stuff. To my opinion, it's not a question of unknown flux, but it's really a real new anomaly in the field. This is my opinion, of course.
I hope you're right. I guess one reason the community isn't discussing it as widely as the other anomalies is because people haven't come up with so many BSM models for it yet.
Thank you, guys.
Yeah, thanks, Marco.
We have one more question. I open the microphone.
I cannot hear the question yet.
It's coming.
It's coming. Yeah. Sorry, but
no worries.
No, the speaker is disappeared. Okay, maybe the question will appear later on Slack. So if there is no other question, let's thank the speaker again, and we can move to the last talk of this session. And I'd like to introduce Gianfranco Bertone.
Hello, everyone. Can you hear me and see me?
Yes, we can also see your slides.
Perfect.
Now they are full screen, so you can start.
Thank you. All right. So, well, let me start by thanking the organizers. It's a pleasure and an honor to speak at this conference series. I've also had the pleasure in the past to meet and interact with Mila Balducciolin, who founded this conference series, and I'm really glad to see that this glorious tradition of this conference is continued, thanks to Mauro Mezzetto and to all the organizers of the conference. I've been asked to speak about the multi-messenger fingerprint of dark matter, and I thought I'd structure the talk as follows. I will start with a short preamble to discuss the so-called dark universe narrative, how we present the history and the status of our field among ourselves as scientists, also to the outside world. And then I will move quickly to the first part of the talk, which is about what we have learned about the nature of dark matter from all the studies we performed over the past 4 decades. And in the second part, I will move to the proper topic of this talk, which is how we can use multi-messenger observations to constrain and hopefully to identify dark matter. So I'll be very quick on this first preamble, because it would be much to say, and we don't really have time in this 30 minutes. But I think the standard way we tell the history of the field of dark matter is, which is usually the usual narrative that you hear at conferences, is that the term dark matter was coined in the 1930s by Fritz Zwicky, and then dark matter was discovered with rotation curves by Vera Rubin, is really a gross oversimplification of what happened in the literature. And just to stimulate your interest in the history of dark matter, let me just mention that more than 100 years ago, at the beginning of the 20th century, Lord Kelvin was applying his kinetic theory of gases to the stars in the universe. So the universe was our own galaxy, basically, but then this is 20 years before we figured out that the Andromeda galaxy was an external galaxy and not included in our own. And so he was really studying the stars in the galaxy as and trying to associate the velocity dispersion of stars with the density of stars. And what he concluded was that many of our stars, and perhaps a great majority of them, may be dark bodies. And only 2 years later, Henri Poincaré was studying the work of Kelvin, and he was explicitly talking about matière noire, first in French, and then dark matter in 1906, and trying to get a sense, trying to estimate what was the amount of dark matter. Another couple of things that are not very much known in our field is that we, even those who admit that Fritz Zwicky was not the first to coin the term dark matter, they think that he was the first to apply the virial theorem to stars or celestial systems. But even that is not true. There's a beautiful paper, for instance, by Albert Einstein in 1921, where he applied the virial theory into a star cluster for completely different reasons. He was looking for a trace of dark energy, as a matter of fact, in these systems, of cosmological constants, I should say, in these systems, and he got a constraint on the number of dark matter in those systems. And even Fritz Zwicky, in the year where he wrote the famous paper on the Coma cluster, he wrote another paper a few months before the Coma cluster paper. But he was talking about something completely different. He was talking about cosmic rays. And you can find this sentence in his paper. He writes, according to present estimates, the average density of dark matter in our galaxy and throughout the rest of the universe are in the ratio of 10 to the 5. Okay, so this is surprising. It is like a time traveler went back and told the actual solution to the problem to Fritz Zwicky. There's a reason why he wrote that. There were estimates of the abundance of dark matter, both locally and on average in the universe. And if you're interested, you will find more information in these 2 papers. Where I'll be happy to continue the discussion on Slack, and or if you have questions after this presentation. Another quick thing I wanted to mention is about the narrative that 95% of the universe is dark. That all of us will have said or heard at some point in our career, and some of us hear and say many times a week, I would say, whenever we speak about that, about the matter and energy budget of the universe. The thing is that, especially when we present this to the general public, we have to, I think, really qualify this statement, otherwise it becomes incomprehensible. And in particular, we need to state that this is only true now, at this particular epoch in the history of the universe, and on very large scales. And if you want to show, especially to an audience of non-experts, what is the abundance of the relative abundance of known matter and unknown matter in the universe, I think you have inevitably to discuss what is the relative contribution of atoms or baryonic matter, dark matter, and dark energy on various scales in the universe. And so the fact that this statement, the statement that 72%, for instance, of the universe in the form of dark energy, is true only if you consider very large scales. So if you're interested, of course, in the expansion rate of the universe, that's the relevant quantity. But if you want to describe, for instance, how galaxies formed or how structures are what is the structure of galaxies, the statement becomes quickly relevant. And without spending too much time on it, you can say the same thing about timescales. If you forget to mention, or if you don't explicitly mention that the statement refers to now and on small scales, the narrative becomes very difficult to understand for the general public, because you would have to explain why the universe went from 100% known at the epoch of Big Bang nucleosynthesis to 95% unknown today, and eventually will become completely unknown. So the only way I think that to explain this in a way that doesn't create more confusion in the mind of people is really to elaborate on the mass and energy evolution of various species in the history of the universe. So what's certainly relevant is that if you want to understand how structures form, if you want to understand how galaxies and stars formed, how any structure formed in the history of the universe, you need to understand, you need to make sense of dark matter, which has dominated the matter component of the universe, matter budget of the universe for a very, very long time, forever, essentially, and it's becoming only the last billion years subdominant, even in terms of energy. Now, the big question, of course, is what is dark matter? And the short answer is that we do not know, but that we have many, many possible ideas of what it could be. In this review article we published a couple of years ago with Tim Tate, we arranged the possible dark matter candidates in different classes. I will not walk you through all the sub bubbles here, but broadly speaking, there could be things like light bosons, and I include here QCD axions and axion light particles and so on. There are neutrinos. I mean, of course, we know the standard model neutrinos contribute a fraction of the dark matter, and then maybe surround neutrinos might contribute a fraction, maybe all, of the rest of the dark matter. There might be a connection with the weak scale in particle physics, and this is probably the field that has attracted most attention in the field, in dark matter searches over the last few decades. And there is the possibility that this is the dark matter is another particle, with completely different properties, and there are many, many ideas also in that sub bubble, let's say. There is still the possibility that dark matter is macroscopic. We've ruled out particles, compact objects, so-called MACHOs, massive compact halo objects, although we know that they contribute a small fraction of the dark matter. This is baryonic matter, of course. But there is the possibility that primordial black holes might contribute, well, some would even say all of the dark matter, although there are more and more stringent constraints on this possibility. And there is still the possibility that we haven't ruled out completely. It's actually very hard, if not impossible, to rule out completely, which is that there might be modified gravity. So the gravity is modified on very large scales in the universe. I would say that the only way of really getting rid of this possibility or excluding this possibility is really finding particles whose relic density, assuming GR, is corresponds to the relic density of dark matter in the universe. Let me go very quickly on this. I don't want to spend too much time in this with this introductory material. Let me just mention that the uncertainty on the properties of dark matter is enormous. So if you just distribute the various candidates that we discussed on the scale and we show them using the dark matter mass as a parameters to classify them, there's an uncertainty on the mass of the dark matter particle over 90 orders of magnitude, 90 orders of magnitude. And this is absolutely insane. You know, I don't think I've ever seen a similar plot in any other field of research. So this is really striking. I think it conveys quite clearly the fact that we are in the dark really about the nature of dark matter. Now, for many years, the leading candidate for dark matter has been have been weakly interacting massive particles, or WIMPs. And the WIMP paradigm was based on a relatively simple idea, which is that these particles were in equilibrium in the early universe, thermal, kinetic, dynamical equilibrium in the early universe with particles of the standard model. And based on some simple arguments, one could conclude that for cross sections at the weak scale, these particles would produce the appropriate relic density in the universe. And the WIMP miracle, so this phrase WIMP miracle was coined in the 90s to precisely to convey this kind of surprising situation in which theories that had been proposed to explain completely different physics, right? The physics, to explain fundamental physical problems like the hierarchy model and fundamental distinction between bosons and fermions and things like that, provided a natural explanation to the dark matter problem in the universe. This has launched an effort that has lasted for many decades. And I think it is fair to say that that no WIMPs has been convincingly, there's no convincing evidence of WIMPs in any of the experiments, accelerator experiments, indirect detection, direct detection, despite many efforts. So the big question is, in a field, are WIMPs ruled out? And my answer to this question is quite simple, and it's a big and resounding no. And it's not because I'm a particular affection for this class of dark matter candidates, but at the simplest level, I think it's quite obvious to anyone who's practicing, who's working in this field, that absence of evidence is different from evidence of absence. And at this level, we have absence of evidence for WIMPs. We haven't ruled out WIMPs as a whole paradigm. Now, of course, this absence of evidence has dampened enthusiasm for WIMPs. But if beyond kind of sociological aspects, I think it's important to understand what the data are telling us. And I think it's fair to say that there are still large portions of the parameter space of specific WIMP candidates that remain viable. There are many papers exploring this possibility. I've listed a few of them here. Another aspect, an important aspect, is that WIMP paradigm is different from WIMP miracle. So you can have WIMPs as dark matter candidates, even if you don't have the surprising coincidence of the fact that these new theories solve at the same time the particle, fundamental particle physics problems and produce via freeze out the correct abundance of dark matter in the universe. There's an interesting paper also exploring this possibility here. And in any case, my impression is that for what concerns WIMPs, there's a clear way forward. We still have 15 years of LHC and high luminosity LHC data ahead of us. The direct detection experiments are continuing their search, and they're going down all the way to the neutrino flow. And there are non-dedicated indirect detection experiments that will continue to provide useful information about the nature of dark matter for years to come. So it's quite obvious to me that we need to continue with those searches. Now, in this review article that I mentioned, we talked about the fact that a new era has come in the search for dark matter, and that our best hope to identify dark matter particles is a strategy that involves broadening and improving and diversifying current searches, 2, exploiting astronomical and cosmological observations, and 3, exploiting gravitational waves as a portal to dark matter. I will not spend too much time on the first point, because there are many talks at this conference exploring many possible ideas to do precisely that, establishing new connections in particular with neutrino physics, and diversifying the uses and the physics you can do, the physics program that you can do with dark matter searches, with dark matter detectors, and so on. So we'll focus instead on point 2 and point 3, in particular exploiting the astro and cosmo observations and exploiting gravitational waves. And let me quickly ask the sorry, how long do I still have? I didn't check.
You have still 10 minutes still. 10
minutes, okay, thank you. Okay, so let me try and give you a sense of what can be done in these two directions. And the way I will do this, I will show you one concrete example in both for both of these points, and then I will provide a review article in each of these subfields for those who want to follow up and know more about what opportunities and challenges we have there. The first point I wanted to make is connected to astronomical observations, and what you see here on this image is the total brightness and color of stars observed by Gaia, and this is the outcome of the release 3, Gaia release 3, that was recently announced. Now, what you can do with these new astronomical surveys is you can obtain the position and the proper motion, the displacement of the of stars, of about 1 billion stars, more than 1 billion stars in our own Milky Way. Now, why is this interesting? Imagine, consider in particular the case of stellar streams. Stellar streams are known structures that we observe in the Milky Way that are produced when a globular cluster, a cluster of stars, enter the potential of the Milky Way and is tidally stripped, forming these very elongated structures in the Milky Way. We observe these stellar streams. We've observed them with astronomical surveys. The thing is, the reason why this is relevant for dark matter is that a standard prediction of dark matter is that, at least of cold dark matter, which is the standard paradigm for the dark matter in the universe, in the standard cosmological model, is that if we could visualize dark matter, we should see a lot of substructures in the distribution of dark matter. And in the standard cosmological model, you can predict what is the mass function of these objects, what is the spatial distribution, and so on. Now, the point of connection between astronomical observations and cold dark matter is that if it is true that there are many of these substructures, then these substructures would perturb these stellar streams, which are very cold systems. The velocity dispersion orthogonal to the direction of the stream is very, very small, and produce gaps or inhomogeneities in the distribution of stars. There is one particular stream that has been observed with Gaia data, and there is actually evidence that this stream is actually perturbed. It presents some gaps and a particular feature, which I don't have time to discuss in detail, which is called a spur. Now, the big question is, can we explain the structure of these distribution of stars in the stream using only baryonic structures, things like globular clusters, molecular clouds that would impact the stream and create gaps and inhomogeneities? And if you plot the power spectrum versus the angle along the stream, you see that the predicted perturbations induced by baryonic structures cannot explain the observed amount of inhomogeneities in these systems. Whereas if you just take a vanilla numerical simulation of the amount of substructures that you have in dark matter, then you can go through the data points quite easily. The uncertainties are still very large, but you can build a self-consistent picture where these the impacts that you observe on the stream are produced actually by dark matter subhalos. And there is this recent paper that was recently accepted on monthly notices. The first author is this brilliant postdoc whose name is Neil Banek. Was a postdoc in Amsterdam, and now he's a postdoc in Texas. And for those of you who are interested in this field, on the many connections between astronomical and cosmological observations and the nature of dark matter, there's a very nice physics reports review article that was put together by Buckley and Peter in 2018, where all these connections are discussed. In the last few minutes, I want to tell you a bit more about yet another frontier, which is the exploration of the exploitation of gravitational waves as a portal to dark matter. Now, we don't have to explain the importance of the detection of gravitational waves that led to the Nobel Prize in Physics in 2017. We observed many systems today, many mergers of black holes, and we also had observed the merger of neutron stars. The question is, can you use this information? Can you use gravitational waves as a portal to dark matter? And the specific connection, there are many connections. The specific one I wanted to highlight today is that it is expected in many different scenarios that the dark matter distribution will be enhanced around black holes. This can happen through the adiabatic growth of the cold dark matter around supermassive and intermediate mass black holes. They can form around primordial black holes as well. And if ultralight bosons exist with a quantum wavelength comparable with the size of black holes, this can also lead to to an overdensity of dark matter around the system. Now, consider this, to understand what is the particular connection here, consider an extreme mass ratio in spiral, where you have a black hole, a central black hole surrounded by dark matter. And then you have a compact object that is merging with the big object. Now you can write down without the energy losses for the system, and because of dark matter, on top of gravitational wave energy losses, energy lost by gravitational radiation, you have dynamical friction induced by dark matter on this secondary object. And this dynamical friction can actually induce a dephasing of the waveform. In order to visualize this is a numerical simulation that shows the interaction of two black holes surrounded by dark matter. And what you see is that the interaction between these two objects, because of the presence of dark matter, is substantially modified with respect to the standard Newtonian case. In standard Newtonian case, these objects would have returned to an elliptical orbit. You see there was a lot of energy loss at the energy center that is reducing the separation and also changing the eccentricity of the orbit. So the problem is quite complicated because you have to solve the merger in presence of this dynamical friction term, and the density itself for dark matter is a function of time. There is a feedback because some of the energy of the binary is transferred to the dark matter distribution. But we've done this, the full exercise, so we could compute, this is the reference to the article, we could compute the dephasing induced by dark matter. And in many systems that are accessible they can be observed with LISA, with the Future Gravitational Wave Interferometer. You should be able to detect these very large dephasing. So I don't have time to go through this connection with primordial black holes. If you have questions, feel free to ask. The only thing I wanted to mention is that for those of you who are interested in the connection between dark matter and gravitational waves, so gravitational wave is a portal for the search for the identification of dark matter. There is this article, this review article, we wrote together with a bunch of brilliant collaborators. This is now published, and it contains many ideas how to establish this connection. So let me conclude. This is a time of profound transformation for dark matter studies in view of the absence of evidence, although we emphasize there's not evidence of absence of popular candidates. The standard detection techniques, accelerator, indirect detection, and direct detection experiments may still reserve surprises. At the same time, however, it is urgent to diversify the dark matter searches. And this conference is a beautiful example of how this is being done by the community, exploiting astronomical observations. And I think what will be important also in the next decade is the exploitation of gravitational waves as a portal for the identification of dark matter. And especially for the young people who are connected, let me mention that this field is completely open, and there's an extraordinary opportunity for the new generations to come with new ideas and discoveries. If I can take 30 seconds to make a quick announcement, I'm looking at the conveners to see if I can take 30 seconds before taking questions.
Yes, you can.
Thank you. I just wanted to flash this slide and announce this workshop. The first annual symposium of UCAPT, that stands for European Consortium for Astroparticle Theory. This is a new initiative with a central hub at CERN. Many of you will probably have heard of it. And I would like to invite you to participate in this conference. There will be also the opportunity to contribute to the collective writing of a white paper about the challenges and opportunities for astroparticle theory in the next decade. Thank you.
Thank you very much for your contribution. We have one question. I will now let the speaker talk.
Hello, can you hear me?
Yes.
Thank you for the nice talk. I just have one question concerning the lack of evidence of WIMPs. So what exactly, in your opinion, would be a solid evidence against the existence of WIMPs, either theoretical or experimental? Thank you.
Yeah, the thing is, WIMPs is not a model. It's like a sort of a paradigm, an idea. And in fact, there are many different possible definitions of WIMPs that you can give. What you can do, and this is part of the standard scientific process, is you can say, what is my theory of a WIMP? Is it a supersymmetric neutralino? Then you have to specify what is your theory, what supersymmetric model you have in mind, what is the value of the parameters, and then you can ask the question, can this be ruled out by experiments? And what has happened so far is that the experiments that have been performed so far have ruled out very large portions of the parameter space, of the so-called natural parameter space of many of these theories, but there are still corners of the parameter space which are perfectly viable. And I mentioned a few articles that actually explore several aspects of these corners of the parameter space. So I think it would be very difficult to rule out in general the idea of WIMPs. You can make it less and less appealing, less and less likely by running experiments for a very long time and excluding larger and larger portions of the parameter space. So that's the best you can do, I think, in our field. If you want to rule it out, you cannot rule out a vague idea. You can rule out concrete implementations of that idea, which is what experiments are currently doing.
Thank you.
Sure.
Is there some other question? We have still a couple of minutes.
Hi, this is Antonio Masiero.
Hello, Antonio.
Hello. Hi, Gianfranco. Thank you for the nice talk. In connection with what you were saying of gravitational waves and dark matter, as you know, there is now a lot of discussion about possible dark matter in the form of primordial black holes. Yes. And I I was also recently hearing some talk about it, and some people are very skeptical about the possibility that the primordial black holes can constitute at least the main source of dark matter. And in any case, gravitational waves could shed some light maybe on this aspect. So I wanted to ask you, in fact, whether this connection between gravitational waves and dark matter, in particular for primordial black holes, could be fruitful, and which road to follow in that direction.
Yes, no, that's a very good question. I didn't have time really to go through it, but I'll give you a short answer, and then maybe we can follow up. So my impression is that primordial black holes with a mass around a solar mass or just below a solar mass are very constrained, very much constrained. So it's very hard to reconcile them with the many constraints, many astrophysical constraints that we have on this possibility. It is still possible, however, that primordial black holes are all of the dark matter if they are very light. If they are just above an asteroid mass, for example, we know that there's a window in mass where this could be all of the dark matter. We don't have many constraints on that possibility. In fact, we had some constraints, some astrophysical constraints, but then people have revised those constraints, and they realized that they weren't as solid and robust as initially thought. So there is a window where there is possible. You will hear people saying that although they are very constrained, there is still the possibility of drawing a mass function. Most of the constraints that you see on primordial black holes as a function, as the dark matter in the universe, they're usually shown in the parameter space of fraction of primordial black holes divided by the fraction of dark matter, and as a function of mass. And this is usually done assuming a monochromatic mass function where all the primordial black holes have a particular mass. Now, it's less obvious than one could naively thought. So naively, you could think that you can distribute these black holes, you can spread them over a very broad range of masses so that they remain subdominant at each particular value of the mass. But in reality, these astrophysical constraints, they are often, but the technical discussion is a bit too long, but the short version is that it is not necessarily the case. So for instance, if you consider microlensing constraints, it's not that you can just have a mass function spread over a couple of orders of magnitude and reduced by 2 orders of magnitude the mass fraction. In fact, for most mass functions, the constraints become even more stringent. So people have played their game. They're playing the game of mass functions. They played the game of invoking clustering also, and the fact that we do not know the major history of these objects over cosmological timescales. So there are some ways to evade those constraints, but those explanations, in my opinion, they're becoming a bit contrived. So the window which remains really open, certainly open, is the one at much smaller values of the mass.
Thank you.
So let's thank the speaker again. The discussion can continue on the Slack channel. We now close this session, and the conference will restart at 5:10 with 3 parallel sessions. The next plenary session will be on Monday at 2 p.m.
Thank you. Thanks again.
Bye to all.